Hey everyone! Today, we're diving into some cutting-edge research in nuclear physics. Recent advanced simulations have shed light on how the viscosity of quark-gluon plasma changes with net-baryon density during heavy atomic nucleus collisions. This research is crucial for understanding the phase transitions of nuclear matter. Let's explore this fascinating topic. Welcome to TrendStorm. Chapter 1. What is quark-gluon plasma? When heavy atomic nuclei collide, they create a fluid-like soup of quarks and gluons, which are the fundamental building blocks of visible matter. This soup, known as quark-gluon plasma, has very low viscosity, meaning it flows with minimal resistance. Researchers have conducted a systematic study to see how this viscosity changes across a range of collision energies. Chapter 2. Viscosity insights from collision data. The research analyzed data from collisions of gold nuclei at various energies. The key finding is that the viscosity of quark-gluon plasma increases with net baryon density, which is the relative abundance of baryons, like neutrons and protons, over antibaryons, produced in the collision. This result aligns with some theoretical predictions but not all, indicating there's still more to learn. Chapter 3. Advanced simulation techniques. The study utilized state-of-the-art viscous fluid dynamic simulations in all three spatial dimensions, combined with newly developed dynamic models of the collision's initial stages. This approach describes heavy ion collisions at the relativistic heavy ion collider, RHIC, over a wide range of energies. By incorporating the evolution of the initial state, the simulations continuously generate fluid nuclear matter as the colliding nuclei pass through each other. This is particularly crucial at lower beam energies, where the assumption of an instantaneous collision doesn't hold. Chapter 4. Event-by-event analysis in nuclear collisions. A team of theorists from Brookhaven National Laboratory, Lawrence Berkeley National Laboratory, the University of California, Berkeley, and Wayne State University performed event-by-event calculations. They considered fluctuations in the initial geometry of the colliding nuclei and the resulting shape of the produced fireball. The researchers varied and constrained the model parameters, including the viscosities of the produced matter and properties of the initial state, to perform a statistical analysis with input from experimental data collected during RHIC's Beam Energy Scan, BESS. This analysis, based on 5 million numerically simulated collision events, provides insights into how viscosities depend on net baryon density. Researchers can now compare these findings to pure theoretical calculations. The same framework can be applied to measurements from BESS Phase 2 at RHIC and the Future Facility for Anti-Proton and Ion Research, FAIR, in Europe. This groundbreaking research enhances our understanding of quark-gluon plasma and its behavior under different conditions. The advanced simulations and event-by-event analysis offer new insights into the viscosities and phase transitions of nuclear matter. Source: U.S. Department of Energy. If you found this video informative, please like, subscribe, and hit the bell icon for more updates on the latest scientific discoveries. Let us know in the comments what you think about this new research and its potential impact on nuclear physics. Thanks for watching, and see you in the next video.